Professor at Dennis Just is an astronomy professor at Pima Community College in Tucson, Arizona. He joined us now to talk some more about this. Thanks for your time.
Thanks for having me, Marilla.
Dennis, what do we learn from this photo?
Ooh, we learn a lot. There's more practical hands-on things like testing Einstein's general theory of relativity. There have been ways to do it, but actually getting an image of the vicinity of a black hole is going to let us do it in unprecedented ways. We also learned...
Go ahead.
Sorry. No, I was going to say, we also learned just the testament of how collaborations work nowadays. I mean, this was something that is remarkable. It took not only a planet-wide network of telescopes, but also a planet-wide network of astronomers and engineers and everybody working on this. And they actually had taken this data 2 years ago and had to go and spend such a significant amount of time to reduce it and analyze it and come up with these amazing things that we see today.
So how many years would you say it took them to get to where they are today? The 2 years?
Well, it's been 2 years since the data was collected. They had gotten all the way up to a petabyte, which is not something we normally encounter in everyday, computers. But the actual experiment itself and the actual Event Horizon Telescope is a decade plus in the making. They've been working on this for a long time. It started off at least since 2008.
Wow. All right. Tell us a bit about black holes. What do they do? How do they work?
So black holes are when essentially all of nature is fighting against gravity when it comes to stars in particular. And so stars are able to overcome gravity by having nuclear fusion explosions essentially happening in their center, and that outward push keeps gravity from crushing them down to an infinitesimal little point. A black hole is when that outward push no longer works, when these stars run out of the fuel to have nuclear fusion go on in them. Now, a supermassive black hole, it's not entirely clear exactly how they form, but it's the same basic principle. It's so much mass shoved in such a tiny space that the gravity is so intense not even light can escape.
So anything that goes towards the black hole, gets close enough, gets sucked in?
Ironically enough, if you get close enough to it, yes. But it's not as though they're these cosmic vacuum cleaners or anything. In fact, if our sun were to turn into a black hole with the same mass, the Earth would continue in its orbit. We'd freeze to death eventually, but it doesn't actually go out and pull you into it.
It would be the cold that would get us. Okay, so moving forward, now having this photo in hand, what will researchers, astronomers be looking to do from here? What's ahead for them?
So at the forefront of physics is understanding how to bring together the two major theories that we have, quantum mechanics and general relativity. And right now they just don't get along. And to bring them together, our theory of gravity, we know, has to be wrong in some sense, and wrong as in it's incomplete. And so there's a million different, alternative versions of gravity that a lot of very smart theorists have come up with. And so I imagine there's going to be a flurry of papers now where people are going to take their theories and compare it with these observations.
Interesting. Dennis Just, I appreciate you hanging out with us tonight. Thanks for your time.
Thanks so much for having me.